Okay, this is a little add-on video for the section on integral test and p-series to cover two examples that are more complicated and definitely beyond what we would normally see in homework or probably even on our test or anything. But let's take a little time to look at these. Determine if this series converges or diverges using both the integral test and the p-series test. All right, so let's actually do the integral test first. That should probably work as is, so let's try that. Okay, for the integral test, we're going to come up with a function for the generating rule, 1 over x squared plus 1. We're going to assert that that is positive, which it is, for x is greater than or equal to 1. We're starting at 1. That's true. And then f is continuous, also for x is greater than or equal to 1. And we'll do the derivative of prime of x. And that is low d high minus, that's a 0, high d low, 2x, over x squared plus 1 squared, which simplifies to negative 2x over x squared plus 1 squared. The top is going to be negative and the bottom positive, so that is less than 0 for x is greater than or equal to 1. So that's true, decreasing. So that means we can say the integral test applies. And then we'll do the integral test. So the integral test would mean we are now writing an integral from 1 to infinity of 1 over x squared plus 1 dx. And making it proper, limit as b approaches infinity, 1 to b of 1 over x squared plus 1. Recognizing that that is the structure for arctangent, so the antiderivative is arctangent of x from 1 to b. So we've got limit as b approaches infinity of arctangent of b minus arctangent of 1. Okay, and the arc whose tangent is 1, the angle whose tangent is 1 is pi over 4. And the angle whose tangent is infinity is pi over 2. So that means that the integral converges. And therefore, the series converges. 1 to infinity, 1 over n squared plus 1 converges by the integral test. Okay, so that's how we would do it with the integral test. Let's go ahead and try to do the p-series test. I'm going to erase all this. Now, this is not a p-series, right? P-series is something of the form n equals 1 to infinity 1 over n to the p power. But the problem is this has this plus 1 here, which is preventing this from being a p-series. But if that plus 1 wasn't there, it could be a p-series. It would be 1 over n squared. 2 is larger than 1. This would be a p-series that converges. Okay. So how can we use p-series to do this? Well, what we can do is say, well, the p-series that's similar to this converges. So we'll be kind of clever about this. Let's try a different series. And that series is going to be similar to the existing series, but we're just going to drop that plus 1, 1 over n squared. And that means that since this one is a p-series with p equals 2, that means that this series n equals 1 to infinity of 1 over n squared converges by the p-series test. Okay, so how does that help us with this series? Well, if you look at this rule, 1 over n squared plus 1, and you look at this rule, which is 1 over n squared, if you add 1 to the denominator, every term in this series is less than every term in this series. And what that means is that if this series is converging over here, if this series is converging to some number, because we just showed, actually, let me use a red pen for that. Right. Okay, if this series over here is converging, then that means all the terms over here are staying underneath the corresponding terms here, because this is always less than that. If this side converges, it squishes this side down, and this side must also converge. So what you can say is, since 1 over n squared plus 1 is less than 1 over n squared, and the series n equals 1 to infinity of 1 over n squared converges, the series n equals 1 to infinity of 1 over n squared plus 1 also converges. Okay, now there's later going to be a specific test called a comparison test that does that more formally, but this is just introducing the idea of that. Okay, let's take a look at one last example. Find the values for p for which this series converge. All right, so this is a little trickier. Now this is not a p series, so they could have just used any constant here. So find the values of this constant where this would converge. This is definitely not a p series or anything close to that. It's not geometric. I think in order for this to converge, we can't use the nth term test for divergence because that is only used for divergence. So we have to use the integral test to analyze this. Okay, so we'll do the integral test, which means that we're going to come up with a function that is this function, x1 plus x squared to the p, where p is just some constant. And then we have to make sure that the conditions are met. So first, is f positive? F is positive. Let's see, this is squared plus 1, that's positive. So this term is positive. X will be positive, certainly for x is greater than or equal to 1, which is where this starts, so that's true. Let's see, f is also continuous. This is essentially, there's nothing in here that's dividing by 0 or logs that have problems with the domain. So that will be continuous for x is greater than or equal to 1 also. And then for decreasing, we can go ahead and do a derivative here. That would require product rule, right, with embedded chain rule. So it's going to be first times the derivative of the second, which is p times 1 plus x squared to the p minus 1, times the derivative of the inside, which is 2x. That's first times derivative of the second, plus the second times the derivative of the first, which is a 1, right? First times derivative of the second, right? So first times derivative of the second plus second times derivative of the first. Wow, okay. And we have to assert that that's negative, all right? So what does that simplify to? Let's see if we can kind of do some combining terms here. We have 2x squared. Now we have a p, 1 plus x squared to the p minus 1. This is just at 1 plus x squared to the p, which means I could, let's see, if there's p of these here and there's one less here, and I could do this. I could say this is 2x squared p, 1 plus x squared to the p minus 1, and say this is 1 plus x squared, and then I take 1 out, and there would be 1 plus x squared. There'd be p minus 1 of those left. So p minus 1 plus another one gives me a total of p of these, which means I can factor this out of both of the terms. So then I would get 1 plus x squared to the p minus 1, and what's left here is 2x squared p plus 1 plus x squared, right? All right, which would be, let's see, we've got 1 plus x squared to the p minus 1. Let's see, this is 2x squared p. This is an x squared term, and that's an x squared term. So there's actually, this is times x squared times 2p plus 1 plus a 1. All right, so if we need all of that to be less than 0, what would need to be true? Let's stop for a second and assume it's true. Okay, so I'm going to assume that this is true, and we'll finish this when we're done. And let's go ahead and just start using this. I'm going to switch colors here. So if I assume this is true, and I say there's an integral from 1 to infinity of the generating rule, x 1 plus x squared to the p dx. Then that means that we would make this proper integral, limit as b approaches infinity of 1 to b x 1 plus x squared to the p dx. Right, now how will I do this antiderivative here? I think I use substitution, so let me do that separately. I'll change colors here. So for the indefinite integral, we've got x 1 plus x squared to the p dx. We'll do a u substitution with that inside 1 plus x squared. So the derivative is 2x, so du is 2x dx. So x dx is 1/2 du. So this becomes u to the p, and this x dx is 1/2 du. And that means the antiderivative is 1/2 u to the p plus 1 divided by p plus 1. And then I'll replace the p with 1 plus x squared. So this is 1/2 1 plus x squared to the p plus 1 divided by p plus 1. Okay, so now that is the antiderivative, and we have to do that. Let me switch back to the other color here. From 1 to b, where b is a limit going to infinity. All right, so we'll have our copy, and remember this is replacing the x here. So this is limit as b approaches infinity of 1/2 1 plus b squared to the p plus 1 over p plus 1, and then minus 1/2 1 plus 1 squared to the p plus 1 over p plus 1. All right, so this one is definitely going to resolve to some number. Really, no matter what p is, this will turn into a number. It really comes down to this term. How can we make sure that this will resolve to a number even when we're plugging up an infinity in here? Okay, so imagine that we can't really plug an infinity in, but imagine this number is getting really big. That means this number is getting very large. The only way that that makes this go to a number is if this moves to the bottom of a fraction, because we can divide by a number and this will converge to 0. So this will converge to 0 if this exponent here is negative, if p plus 1 is less than 0. In other words, if I subtract 1, p has to be less than -1. Right, so I think that is actually the value for which this series will converge. This is the answer, that if p is less than -1, this term converges, therefore the integral converges, therefore the series converges. Now, we did make the assumption that this is true, so let's see if that would be true if p was less than -1. Okay, if p was less than -1, this term would be 1 plus x squared. If p is less than -1, this is some sort of negative number here, right? And then we've got, let's see, x squared, and this 2 times p plus 1. If p is less than -1, that means that this is a negative number in here, plus a 1, right? And I think in this case, let's see, yeah, I think I ended up, check x squared. Yeah, we have to be able to assert that this is negative. I believe this one is a positive value to a negative, so that is 1 over a positive value. So this part's positive. The question is this. We're saying that this is producing a negative. That is a positive value, right? So as long as this term is numerically larger than 1, this will be a negative. And that will be true. If not for 1, it'll be true for 2. So this definitely is a positive times a negative, and therefore this is true, at least starting with the second term. So that means that we have verified that the thing we assumed that the integral test applied is true. All right, that's a pretty convoluted problem. Not really sure why we included that, because that's way harder than anything we would have in homework or on our test. It was from our textbook, which is interesting, but I've never seen anything of this complexity even on the AP exam. Okay, but still an interesting problem to consider. All right, that's it for the supplemental additional examples.